So in the early mid-'80s, 1983 to 1985, I was the lead product designer at Thinking Machines Corporation, which was formed solely to build the doctoral thesis of Danny Hillis. He was a doctoral candidate under Marvin Minsky, and his doctoral thesis was called The Connection Machine. And it was an idea for a massively parallel artificial intelligence supercomputer. And when he decided to build it, it coincided with the exact time when I graduated from my master's in mechanical engineering at MIT. We had been friends because I was let's say, a MIT AI lab social groupie. They threw the best parties. And so I had spent the last couple of years in this atmosphere of discussions about artificial intelligence. I had also spent half my classes at what became the Media Lab, the Architecture Machine Group and the Visual Language Workshop. And so 3 days or so after my graduation ceremony, Danny said, you know, I've been working on this concept for the connection machine. I'm starting a company to build it. Will you come and be the product design engineer? Because we don't know if it's physically possible to build it. And he told me from the beginning in that first conversation, and if you come, you get to work with Richard Feynman, the Nobel Prize physicist. And that decided, I said, immediately, where do I sign? Where do I sign? So it really happened that way. It was a small group of people at first, and Richard Feynman was already designing the router between the 65,000 plus processors that were making up this connection machine. Danny's idea was that, you know, at that time, supercomputers had one, maybe two, if they were considered parallel processors, maybe four. But he wanted to go to a massively parallel machine with a completely different architecture that was structured after the human brain. So the first job was to take all the information that came from the electrical engineers about the size of the boards, the number of the cable connections, etc. And I said, okay, you know, taking all the components you're talking about, it's a machine that's 10 feet high and, you know, about 5 feet by 5 feet, you know, so what is that, over 3 meters and very large. And then they said, oh, we can't do that, and went back and were able to reduce down to a much smaller size. So in the meantime, however, Danny said, well, you're going to have to, you know, figure out how to wire all these connections, talk to Richard Feynman, who's designing the router that connects all of these processors. So I talked to him, and he said, oh, it's easy. It's a 12-dimensional Boolean n-cube. And I said, well, okay, what's that? And he said, oh, it's easy. I'll just draw it for you. And he started drawing the connections, and I'm going to radically reduce it. Basically, he drew the 1D connections, the 2D connections, the 3D, which looked like a cube, and then the 4D, which was a cube inside of a cube. And then he said, after that, it gets too complicated to draw. And I was going like, oh, that's great. Well, I'm going to have to figure it out because I have to be able to tell the electrical engineers where all the connections go. And I played around with it on paper and pencil. We were designing the machine like analog on paper and pencil on a drawing board. And playing around with it with the topology, I finally realized I could take the inner cube, set it next to the outer cube, keeping all the connections, and it looked like a 1D cube, just 2 cubes connected to each other with a line. And you double that to get a 5D cube, then you have what looks like a square. You double that to get a 3D cube, and it looks like a cube of cubes. And I realized every 3 dimensions, this structure repeats. So the 12D cube is made out of a cube of 9D cubes, made out of a cube of 6D cubes, made out of a cube of 3D cubes, made out of a cube of the actual processor chips connected to each other. With that, it was really easy to make the connections. So we had all these concepts running, and then at some point, Danny and I started talking about a t-shirt. And he said, you know, the concept that I have of the machine, really what makes the machine different from all other attempts so far, is that there's this hardware structure, this hardware structure, but the software structure can make data connections independently of the hardware structure. And so I said, well, okay, then let's represent the hardware structure with a cube of cubes that I had already come up with and was able to draw. And then let's represent the software structures by these, soft sort of pom-poms and then their soft connections going between them. So this logo for the CM1 t-shirt really was the first depiction of the unique aspect of that computer design. And when I went to say, okay, let's make the final machine, what does it actually look like? We had been talking about the cube of cubes for quite a while at that point, and we hired two industrial designers, Al Hawthorne and Gordon Bruce, then initially from Elliott Noy's design company, to work with us on the machine. I found out years afterward that Al had actually done the first concept sketches for 2001: A Space Odyssey. He wasn't involved in the actual implementation of the sets, but the first concept sketches, and then the two of them together, Al and Gordon, had actually done the interior design of the first space lab, which you might remember is the first sort of permanent orbiting space lab in the world. So it turns out they had these science fiction connections, which I didn't know about at that time, but that would also explain why they were very comfortable with this sort of sea of ideas that were floating around in the company that I had also sort of grown up with in science fiction and looking at 2001: A Space Odyssey, and then, all of these science fiction stories of intelligences helping us conquer space and sort of grow beyond the physical limits of our bodies here on Earth. And certainly at that point, even though the film 2001 was made in 1968, and we're now talking about 1983, 84, that was still the dominant imagery for artificial intelligence, for a general artificial intelligence, which ran the ship, the AI that ran the ship, and that turned against the human astronauts because the general AI saw the humans as endangering the mission that he was programmed to carry out. So we were very conscious of this concept of AI as being something that could become terrifying, could take over, could endanger humans. And we were very concerned because of that when we say that we are going to create this AI supercomputer, that we want to explain what it is, why it's an AI, and also emphasize that we saw AI as a tool to help humans and not to conquer them and dominate them. So for instance, Danny said one thing he'd really like to do is keep the machine under my height. Now I'm 160 centimeters. I'm a relatively small, half Asian American woman. And so he said, if it's your height or so, that's under the eye level of most white American males. And so it'll be perceived as a member of the family rather than as some sort of scary overlord. So yes, all of these conversations were, I would say, in pretty much exactly the same form going on in the 80s. It's just that, the machine was also being used to program neural nets, etc. But it was always clear to everyone back then that the number of layers that we could implement in neural nets was far too few in order to actually get the sort of results that people had hoped for. So that only happened, really, I'd say in 2012. And remember, we're talking mid-80s right now. What was an image besides 2001 was that, earlier mainframe computers would always have a panel of lights. And in fact, did you? 1982. Okay, so Blade Runner came much later. But mainframe computers always had some lights to give status information. And so what we decided to do with the connection machine, I mean, at some point we investigated very different forms, but at some point it became clear that the cube of cube concepts and the T-shirt logo as a depiction of that were really the fastest, most pointed explanation of the important differences between this new machine and all the other existing machines. And because we wanted to bring in someone from a company or an agency and say, just write a check for $3 to $5 million and you get a machine like you've never seen before, the machine you've always dreamed of, it had to look different. It had to look striking. It had to explain itself in an instant. And so we actually decided to implement it in the form of the T-shirt. So the final machine that you see a photograph of in the vitrine has a shape of a black cube of cubes. So there's a total of eight cubes. And then the front and back sides of the machine, the doors are translucent so that the status lights inside the machine could show through and you would see the machine thinking as the status lights blinked. And to make it easier to see, those status lights, which are usually next to each processor chip, we moved them forward to the edge of the board. So what you see is you see 4,096 lights, each of them directly wired to a processor chip. Each chip had 16 processors, by the way. And so you can program them any way you want, but if you program them according to my concept, then if you're using all the processors all the time, then all the lights should be lit up. At some point, the president, Cheryl Handler, said, can't you make them blink in a random and pleasing manner that makes them look like a little bit more like they're working? And so someone did indeed write a program called Random and Pleasing. My friend Dan Aronson implemented it for the CM2, and it actually sort of blinks the lights. And if we show the machine today, the machine hasn't really worked probably since about 2000. So when we show the machine today and it has blinking lights, it's actually a grid of hardware LEDs that we put on between the boards and the doors to simulate that. But what was really important is that if you have the machine without the lights on, which is how it was exhibited in a lot of different computer museums, the machine looks dead. And the whole reason for this design was to show that the machine was alive and thinking, that it was like a huge electronic brain that was thinking as you watch. So that's the very first machine with restored simulated lights was when I got one of these machines into the Museum of Modern Art in New York, because it was in the design department, and they said, you know, it's an important part of the design. We're willing to spend the money to implement this hardware simulation. So what you see in the vitrine is you see the sketches of the one-dimensional to 2 to 3 to 4 to 5 to 6 to 9 to 12 dimensions. And you'll note that it was drawn by hand on paper. And then some other sketches showing how the cables ran inside the machine and on the boards and between the boards inside the machine. And then photographs of the actual first prototypes. There's really just a metal structure that I attached the backplane boards to and was trying to develop the cable foldings. So my Japanese origami background came in good stead as I was trying to pack all of these cables into the machine. And then you see a photograph of the final machine, the black cube of cubes with the blinking lights in the front and back of the machine. And you see a photograph of me wearing the T-shirt, and which we had in the meantime renamed the CM1 Feynman t-shirt because in 1998, Apple came out with this Think Different campaign, and one of the images that they used, besides Martin Luther King and Gandhi, was Richard Feynman wearing my t-shirt. He loved it. He wore it for a lot of his lectures. And so we all went and posed in our t-shirts. And there's a backstory to that I didn't know at the time. But my friend Joanna Hoffman who I got to know in Silicon Valley. I was working at Hewlett-Packard. She was working for Apple, but she couldn't tell me what she was working on. After 1984, she told me she was working on the very first Macintosh. So she was known at Apple as the only woman who could say no to Steve Jobs, very strong personality. And she told me years later that when Steve Jobs first saw a photograph of the CM1 connection machine, he said to her, "Bring me the designer. I want him to design my next computer." Jobs had been thrown out of Apple and had started his next computer company. And in those days, I was already in Germany being an art student. Germans did not have email. So I was cut off my entire life. Germans, Austrians, Europeans only got email basically in the mid-90s. And we're talking, you know, the mid-80s right now. So she had no way of contacting me. I had lost touch with that entire part of my life. But if you look at the next cube, it was a perfect black cube, a single cube. And if you look at all the designs he did before, they were these sort of beige, kind of rounded edges, kind of cuddly boxes, including the first Macintosh. Yeah. Everything he did after the next cube and everything after had this, what I like to call the technological sublime, had an aesthetic that makes you think, with this object, I can become more than my physical body. I can do things that I can't do without this object. I need this object. And, and this is my own sort of, you know, looking at the corollaries. But when Paola Antonelli from the Museum of Modern Art in New York was interested in acquiring a machine, I told her this story. She called Joanna Hoffman directly and corroborated, and Joanna and Paola both think that this really was a watershed moment that changed Steve Jobs' design. The other thing that I didn't find out until I started researching the machine to get all sorts of background information that I could submit to MoMA as a package. Why should they acquire this machine? Is I went back and I talked to Danny. And at that point, all of the information that I could find on the internet about the connection machine, about Thinking Machines Corporation, said it was a failure. It went bankrupt in the mid-90s. It was a dead end. It was a failure. We're talking 2015 right now. I went and talked to Danny. My first question was the machine really a dead end? Was it really a failure? And he rolled his eyes and told me, well, it turns out that Sergey Brin, the co-founder of Google, learned parallel programming on a connection machine too as a bachelor's student. And Danny himself had gone on after the bankruptcy of Thinking Machines to start a company called MetaWeb that did what was called semantic networks. So he said the hardware was one part, but you need these semantic networks that understand the structure of human language and can make inferences on the meaning of a sentence. And that company was started in 2005, was bought by Google in 2010. Danny's co-founder, John Gianandrea, at that point then joined Google as the head of Google Search, and then shortly thereafter, the head of Google AI. Also, if you know your algorithms, there's two algorithms that made Google the powerhouse it was. The PageRank, kind of named after Larry Page, that decided how to rank pages, and MapReduce. MapReduce is a concept from Lisp that Danny talks about in his book, The Connection Machine. Alpha mapping, taking information, sending it out to all the processors in the machine. Beta reduction, taking the results of all those calculations, those separate calculations, up 65,000 of them if you have that machine, and reducing them to a single answer or a single answer set. MapReduce was patented by Google in a slightly controversial patent. And those two algorithms were the secret of Google's success as a search engine and then as an AI giant. This is a history of AI that is not known because the company Thinking Machines dispersed, and it turns out none of the scientists is really the type who wants to go out and get publicity, and there was no marketing person. So this was news to me in 2015 when I found this information from interviewing Danny and Brewster Kahle and Lou Tucker, other people who worked on the original machine. And it's an unknown key moment in the history of artificial intelligence supercomputing.
Do you want to tell the story? Because you
I tell the story as best I can. I've got interviews with Danny, for instance, on the internet. But who am I to tell the history of computing technology experts that they're missing a huge chunk of computer history? I'm now looking for someone who has the credentials to look at that and write that history and talk to the people who are still alive, who worked on the connection machine and who understand how that technology developed, if you will, in the background from the mid-90s to around 2012 or so, when ImageNet and Geoffrey Hinton's work then started bringing the current state of computing and all of these ideas that had been around for decades together and making them work. That's the point. In 2012 is the point when the current generation of artificial intelligence machines started really being able to fulfill the promise of artificial intelligence in the 80s that we were working on at Thinking Machines. I mean, I started out as a Stanford product design graduate in 1979. I worked in Silicon Valley for Hewlett-Packard, just doing the packaging design of computer terminals. Those things that kind of look like what a PC looks like today, except in those days it was connected to a mainframe behind closed doors. And that's the time I was in Silicon Valley. I got to know Joanna, basically because both of our boyfriends were working at Xerox PARC, Palo Alto Research Center, which is where the mouse was invented, windowing was invented, etc. So I knew of this very fertile atmosphere, especially around AI and new computing concepts, but my background was not in AI, not in computing at all. It was in mechanical engineering product design. And I didn't see a place for me in Silicon Valley at that time. So I went to graduate school at MIT. That's where I discovered this part of the architecture department that became the Media Lab after I graduated. And that's when I started working with computer graphics and with images again, and started really thinking that I wanted to become a media artist, specifically artist. Yeah. And so I had been planning actually on maybe going to art school as soon as I graduated from MIT. I talked to friends of mine who were founding the Media Lab at that point, and they told me literally, if you want to do art, the Media Lab is not the place for you. The Media Lab, MIT, is to build tools that other people, maybe also artists, can use. Yeah. So I already had one, so to speak, one refusal there. And then the 2 years I spent at Thinking Machines were kind of an accidental detour. But in those 2 years, they gave me carte blanche. They said, you know, this machine is going to cost $3 to $5 million. So the amount you spend on packaging is so negligible. Just make it really fantastic. And so I spent the whole time thinking about what does AI mean to us, you know, and of course, you know, growing up in the US, you have the classical Greek mythology, so you have Prometheus, how he created mankind, brought them technology, fire, and was punished by God, by Zeus for that. You also have the story of Gollum, which in Jewish thought then a very holy rabbi could create life, but it could go wrong, but only really someone who's very, very skilled can control that. But you also have my Japanese background. And if you know anything about Japanese or Asian religion in general, it's actually very animist. So in Japan, you'll see a sacred rope around a tree or a stone. You'll see a sword venerated. All of these, what we consider in the West to be inanimate objects, are venerated as objects of power that somehow have some sort of spirit inside. And that's why the Japanese are in love with robots. We're in love with robots even in those days, even after being bombed by the worst technology the world has ever invented, nuclear bombs. So from that standpoint, if a rock or a sword or a tree can have a spirit, why not a machine? Why not? Why can't a robot be alive? Why can't a machine be alive? So these are the cultural influences that flowed into my thinking. And then also because you talked about other cultural influences like maybe Blade Runner or so, like I said, that came later. Yeah. But what did influence me was the sculptures of Arnaldo Pomodoro, which gives you the idea that maybe we can build our own planets. We can build our own mechanical civilizations that also flowed into this image of the connection machine. And Alan Gordon really captured that very well. If you look at between all of the cubes, the gratings have these fingers that interlace. And I would have never done that because I thought, oh, it'd be too expensive, we can't do that. And they were, you know, they said, no, it's okay, we're going to just spend the money and make it look good. So there's also this sort of grating that you see very much in Arnaldo Pomodoro's work, which comes out in the machine. So yes, there's all of these science fiction images that flow into the machine, but you know, these also the Judeo-Christian culture, but also my Japanese, Asian, Shinto, Buddhist culture that flow into that machine.